The derivative of a function of a real variable measures the sensitivity to change of a quantity which is determined by another quantity. Derivatives are a fundamental tool of calculus. For example, the derivative of the position of a moving object with respect to time is the object's velocity. This measures how quickly the position of the object changes when time is advanced. The derivative of a function of a single variable at a chosen input value, when it exists, is the slope of the tangent line to the graph of the function at that point. The tangent line is the best linear approximation of the function near that input value. For this reason, the derivative is often described as the instantaneous rate of change. The ratio of the instantaneous change in the dependent variable to that of the independent variable. Derivatives may be generalized to functions of several real variables. In this generalization, the derivative is reinterpreted as a linear transformation whose graph is the best linear approximation to the graph of the original function. The Jacobian matrix is the matrix that represents this linear transformation with respect to the basis given by the choice of independent and dependent variables. It can be calculated in terms of the partial derivatives with respect to the independent variables. For a real-valued function of several variables, the Jacobian matrix reduces to the gradient vector. The process of finding a derivative is called differentiation. The reverse process is called antidifferentiation. The fundamental theorem of calculus states that antidifferentiation is the same as integration. Differentiation and integration constitute the two fundamental operations in single-variable calculus. Differentiation and derivative. Differentiation is the action of computing a derivative. The derivative of a function f of a variable x is a measure of the rate at which the value of the function changes with respect to the change of the variable. It is called the derivative of f with respect to x, if x and y are real numbers, and if the graph of f is plotted against x, the derivative is the slope of this graph at each point. The simplest case, apart from the trivial case of a constant function, is when y is a linear function of x, meaning that the graph of y divided by x is a line. In this case, y equals f equals mx plus b, for real numbers m and b, and the slope m is given by where the symbol delta is an abbreviation for change in. This formula is true because thus, since it follows that this gives an exact value for the slope of a line. If the function f is not linear, however, then the change in y divided by the change in x varies. Differentiation is a method to find an exact value for this rate of change at any given value of x. The idea, illustrated by figures 1 to 3, is to compute the rate of change as the limit value of the ratio of the differences delta y, delta x. As delta x becomes infinitely small. Notation. Two distinct notations are commonly used for the derivative, one deriving from Leibniz and the other from Joseph Louis Lagrange. In Leibniz's notation, an infinitesimal change in x is denoted by dx, and the derivative of y with respect to x is written suggesting the ratio of two infinitesimal quantities. In Lagrange's notation, the derivative with respect to x of a function f is denoted f, or fx, in case of ambiguity of the variable implied by the derivation. Lagrange's notation is sometimes incorrectly attributed to Newton. Rigorous definition. The most common approach to turn this intuitive idea into a precise definition is to define the derivative as a limitive difference quotients of real numbers. This is the approach described below. Let f be a real-valued function defined in an open neighborhood of a real number a. In classical geometry, the tangent line to the graph of the function f at a was the unique line through the point that did not meet the graph of f transversely, meaning that the line did not pass straight through the graph. The derivative of y with respect to x at a is, geometrically, the slope of the tangent line to the graph of f at. The slope of the tangent line is very close to the slope of the line through, and a nearby point on the graph. For example, these lines are called secant lines. A value of h close to 0 gives a good approximation to the slope of the tangent line, and smaller values of h will, in general, give better approximations. The slope m of the secant line is the difference between the y values of these points divided by the difference between the x values, that is, this expression is Newton's difference quotient. Passing from an approximation to an exact answer is done using a limit. Geometrically, the limit of the secant lines is the tangent line. Therefore, the limit of the difference quotient as h approaches 0, if it exists, should represent the slope of the tangent line too. This limit is defined to be the derivative of the function f at a. When the limit exists, f is said to be differentiable at a. Here f is one of several common notations for the derivative. Equivalently, the derivative satisfies the property that which has the intuitive interpretation that the tangent line to f at a gives the best linear approximation to f near a. This interpretation is the easiest to generalize to other settings. Instead, define q to be the difference quotient as a function of h. Q is the slope of the secant line between, and, if f is a continuous function, meaning that its graph is an unbroken curve with no gaps, then q is a continuous function away from h equals 0. If the limit lim(h0q) exists, meaning that there is a way of choosing a value for q that makes q a continuous function, then the function f is differentiable at a, and its derivative at a equals q. In practice, the existence of a continuous extension of the difference quotient q to h equals 0 is shown by modifying the numerator to cancel h in the denominator. Such manipulations can make the limit value of q for small h clear even though q is still not defined at h equals 0. This process can be long and tedious for complicated functions, and many shortcuts are commonly used to simplify the process. Definition over the hyperreals relative to a hyperreal extension are r* of the real numbers. The derivative of a real function y equals f at a real point x can be defined as the shadow of the quotient increment y, increment x for infinitesimal increment x, where increment y equals f. Here the natural extension of f to the hyperreals is still denoted f. Here the derivative is said to exist if the shadow is independent of the infinitesimal chosen. Example: the squaring function f equals x2 is differentiable at x equals 3, and its derivative there is 6. This result is established by calculating the limit as h approaches 0 of the difference quotient of f. The last expression shows that the difference quotient equals 6 plus h when h0 and is undefined when h equals 0, because of the definition of the difference quotient. However, the definition of the limit says the difference quotient does not need to be defined when h equals 0. The limit is the result of letting h go to 0, meaning it is the value that 6 plus h tends to as h becomes very small. Hence the slope of the graph of the squaring function at the point is 6, and so its derivative at x equals 3 is f equals 6. More generally, a similar computation shows that the derivative of the squaring function at x equals a is f equals 2a. Continuity and differentiability: if y equals f is differentiable at a, then f must also be continuous at a. As an example, choose a pointer and let f be the step function that returns a value, say 1, for all x less than a, and returns a different value, say 10, for all x greater than or equal to a. F cannot have a derivative at a. If h is negative, then a plus h is on the low part of the step, so the secant line from a to a plus h is very steep. And as h tends to 0, the slope tends to infinity. If h is positive, then a plus h is on the high part of the step, so the secant line from a to a plus h has slope 0. Consequently, the secant lines do not approach any single slope, so the limit of the difference quotient does not exist. However, even if a function is continuous at a point, it may not be differentiable there. For example, the absolute value function y equals x is continuous at x equals 0, but it is not differentiable there. If h is positive, then the slope of the secant line from 0 to h is 1, whereas if h is negative, then the slope of the secant line from 0 to h is negative 1. This can be seen graphically as a kink, or a cusp, in the graph at x equals 0. Even a function with a smooth graph is not differentiable at a point where its tangent is vertical. For instance, the function y equals by 1/3 is not differentiable at x equals 0. In summary, for a function f to have a derivative, it is necessary for the function f to be continuous, but continuity alone is not sufficient. Most functions that occur in practice have derivatives at all points or at almost every point. Early in the history of calculus, many mathematicians assumed that a continuous function was differentiable at most points. Under mild conditions, for example if the function is a monotone function or a Lipschitz function, this is true. However, in 1872 Weierstrass found the first example of a function that is continuous everywhere but differentiable nowhere. This example is now known as the Weierstrass function. In 1931, Stefan Banach proved that the set of functions that have a derivative at some point is a meager set in the space of all continuous functions. Informally, this means that hardly any continuous functions have a derivative at even one point. The derivative is a function. Let f be a function that has a derivative at every pointer in the domain of f. Because every pointer has a derivative, there is a function that sends the pointer to the derivative of f at a. This function is written f, and is called the derivative function or the derivative of f. The derivative of f collects all the derivatives of f at all the points in the domain of f. Sometimes f has a derivative at most, but not all, points of its domain. The function whose value at a equals f, whenever f is defined and elsewhere is undefined, is also called the derivative of f. It is still a function, but its domain is strictly smaller than the domain of f. Using this idea, differentiation becomes a function of functions. The derivative is an operator whose domain is the set of all functions that have derivatives at every point of their domain and whose range is a set of functions. If we denote this operator by d, then d is the function f. Since d is a function, it can be evaluated at a point a. By the definition of the derivative function, d equals f. For comparison, consider the doubling function f equals 2x. F is a real-valued function of a real number, meaning that it takes numbers as inputs and has numbers as outputs. The operator d, however, is not defined on individual numbers. It is only defined on functions. Because the output of d is a function, the output of d can be evaluated at a point. For instance, when d is applied to the squaring function, x(x2), d outputs the doubling function x2x, which we named f. This output function can then be evaluated to get f equals 2, f equals 4, and so on. Higher derivatives let f be a differentiable function, and let f be its derivative. The derivative of f is written f, and is called the second derivative of f. Similarly, the derivative of a second derivative, if it exists, is written f, and is called the third derivative of f. Continuing this process, one can define, if it exists, the nth derivative as the derivative of the th derivative. These repeated derivatives are called higher-order derivatives. The nth derivative is also called the derivative of order n. If x represents the position of an object at time t, then the higher-order derivatives of x have physical interpretations. The second derivative of x is the derivative of x, the velocity, and by definition this is the object's acceleration. The third derivative of x is defined to be the jerk, and the fourth derivative is defined to be the jounce. A function f need not have a derivative, for example, if it is not continuous. Similarly, even if f does have a derivative, it may not have a second derivative. For example, let calculation shows that f is a differentiable function whose derivative is f is twice the absolute value function, and it does not have a derivative at 0. Similar examples show that a function can have k derivatives for any non-negative integer k but no th-ordered derivative. A function that has k successive derivatives is called k times differentiable. If in addition the kth derivative is continuous, then the function is said to be of differentiability class Ck. A function that has infinitely many derivatives is called infinitely differentiable or smooth. On the real line, every polynomial function is infinitely differentiable. By standard differentiation rules, if a polynomial of degree n is differentiated n times, then it becomes a constant function. All of its subsequent derivatives are identically 0. In particular, they exist, so polynomials are smooth functions. The derivatives of a function f at a point x provide polynomial approximations to that function near x. For example, if f is twice differentiable, then in the sense that if f is infinitely differentiable, then this is the beginning of the Taylor series for f evaluated at x plus h around x. Inflection point 8 point where the second derivative of a function changes sign is called an inflection point. At an inflection point, the second derivative may be 0, as in the case of the inflection point x equals 0 of the function y equals x3. Or it may fail to exist, as in the case of the inflection point x equals 0 of the function y equals by 1/3. At an inflection point, a function switches from being a convex function to being a concave function or vice versa. Notation. Leibniz's notation. The notation for derivatives introduced by Gottfried Leibniz is one of the earliest. It is still commonly used when the equation y equals f is viewed as a functional relationship between dependent and independent variables. Then the first derivative is denoted by and was once thought of as an infinitesimal quotient. Higher derivatives are expressed using the notation for the nth derivative of y equals f. These are abbreviations for multiple applications of the derivative operator. For example, with Leibniz's notation, we can write the derivative of y at the point x equals a in two different ways. Leibniz's notation allows one to specify the variable for differentiation. This is especially relevant for partial differentiation. It also makes the chain rule easy to remember. Lagrange's notation, sometimes referred to as prime notation. One of the most common modern notation for differentiation is due to Joseph Louis Lagrange and uses the prime mark, so that the derivative of a function f is denoted f, or simply f. Similarly, the second and third derivatives are denoted and to denote the number of derivatives beyond this point. Some authors use Roman numerals in superscript, whereas others place the number in parentheses. Or the latter notation generalizes to yield the notation f for the nth derivative of f. This notation is most useful when we wish to talk about the derivative as being a function itself. As in this case, the Leibniz notation can become cumbersome. Newton's notation for differentiation, also called the dot notation, places a dot over the function name to represent a time derivative. If y equals f, then and denote, respectively, the first and second derivatives of y with respect to t. This notation is used exclusively for time derivatives, meaning that the independent variable of the function represents time. It is very common in physics and in mathematical disciplines connected with physics such as differential equations. While the notation becomes unmanageable for high-ordered derivatives, in practice only very few derivatives are needed. Fluent inflections. Newton tried to explain calculus using fluent inflections. He said that the rate of generation is the fluxion of the fluent, which is denoted by the variable with a dot over it. Then the rate of the fluxion is the second fluxion, which has two dots over it. These fluxions were thought of as very close to zero but not quite zero. But when you multiply two fluxions together you get something that is so close to zero that it is treated as zero. Newton took derivatives by replacing all the x values with and all the y values with, and then used derivative rules to take the derivative and solve. For here is an example, using the fact that we can see and so. Newton described mathematical quantities to be like continuous motion. This motion, he said, could be thought of in the same way that a point traces a curve. He defined this quantity and called it a fluent. He went on to name the rate at which these quantities change. Newton called this the fluxion of the fluent, and he represented it by. So, if the fluent was represented by x, Newton denoted its fluxion by, the second fluxion by, and so on. This can be related to the modern language we use to describe derivatives. In modern language, the fluxion of the variable x relative to an independent time variable t would be its velocity dx, dt. In other words, the derivative of f with respect to time t is dx, dt. Moment of the fluent Newton called ρ the moment of the fluent. The moment of the fluent represents the infinitely small part by which a fluent was increased in a small time interval. Once he allowed himself to divide through by O, Newton decided it was justifiable to drop all terms containing O. Euler's notation uses a differential operator d, which is applied to a function f to give the first derivative df. The second derivative is denoted d2f, and the nth derivative is denoted dnf. If y equals f is a dependent variable, then often the subscript x is attached to the d to clarify the independent variable x. Euler's notation is then written or, although this subscript is often omitted when the variable x is understood. For instance, when this is the only variable present in the expression. Euler's notation is useful for stating and solving linear differential equations.